Welcome. Those of you who are devotees of the MuzMath Rocking channel are going to be excited to know that we've combined with what we call BackHallProductions to do some of our videos in a personally expressive way, which means you're going to see me. This is my back hall. I've moved all the coats out and we're going to do a little bit of math for you. So what I want to do today is show you how a derivative can help answer a question we've already been looking at this year. And it's going to be one of those optimization ones. It's going to be the classic fold up the corners of the box. So we're talking about starting. Here's our question. Question EQ. We'll call it a question example, the EQ. All right, since I just made that up. We're talking about a 20 by 20 piece of metal. We want to cut a square corner for each one of them and then fold it, as you remember, along the dotted lines to create a box. We want to write an equation or a function for the volume of that box. And then that was our function writing unit. And then we took a look at how could you figure out when that volume could be biggest, what are the dimensions? Well, that's what we're doing today. So let's quickly go into that. I'm going to put an X right here, which means it goes here, here, and here, as you know. Now that means then, since this is a square, we know that this side would be 20 minus 2x, and so would this. Oh, that marker's getting old. All right, so when we fold up the corners, we're now talking about a box that looks like this. It's got a height of x, a 20 minus 2x, and a 20 minus 2x. This is something we did earlier. So there's a function to be written for the volume here. V of x. Well, quite simply, it's length times width times height. But I'm going to write it this way. Now, as you remember, when we wrote functions, we needed to define a domain. So I'm going to do that over here so it's visible. The domain. Well, when you think about it, basically, x must be greater than or equal to 0 because you don't want to have, can you see me, hopefully? You don't want to have less than 0 because it'd be a negative. 0 is okay, the volume's 0. If you don't cut anything out, it's not a good box, but it's not a problem for our domain. And on the other side, if I cut towards the middle, if this equals 0, it's because I had two 10s, so it's got to be that. Now, with this comes the idea that this is a cubic. Double root at 10, so it bounces. Another 0 here, and it's got a negative times negative, so positive x. So this was, from our earlier stuff this year, what our graph would look like if we were graphing the entire function. But we're not graphing the entire function. We're only going to graph the part over the domain. So I'm going to write the domain or the drawing in a little bit here. Again, a sort of a abbreviated one, but let's do some algebra here first. V of x equals x times 400 minus 80x plus 4x squared. Distributing the x and rewriting it in a typical polynomial fashion, descending order, we get to here. Now, in our pre-calc stuff, this was a better way to write it because we could do this graph and think about it. All right, so now we have this, and our domain, I'm going to put it right here, is 0 to 10. That's another way of telling people the interval they should consider this function. Now, if we go back to what we did earlier this year, the graph that should go with this in our minds would be only something from 0 to 10. The volume here and the x here. That is, as you can see over here, hopefully, I don't know if that's in the way or not, hopefully not, is this part right here. So, I'm going to draw that. And it's not a parabola, remember that, so it may or may not be symmetrical. That was a pretty bad drawing, but there it is. We'll go with that. What we did earlier this year was we used our calculators and the idea of second calculator max to get that. Well, today I'm going to show you how calculus, the derivative, can help you find that. Because what we know right here, if you think about it, is it's the turning point where it stopped going up and went down, and its slope would be 0 because the tangent line would be horizontal. Now remember, there were 2 of them in this case, but we don't care about this one, right? That's not going to be the max. We know that. It's where it bounced back up. You wouldn't want to look at the whole graph because this, what we call a relative max here, is an absolute max here. And that's what we're looking for, the absolute maximum volume, so we can get the optimal dimensions. We did all this earlier, but you would have gone to a calculator. Now you can go to calculus. I know the slope of the curve is 0 here. That means I'm interested when is v prime of x equal to 0. V prime is really easy here because we wrote it as a polynomial. You can see why we didn't leave it here. I will be doing the product and quotient and chain rules with you, but right now we don't have those rules, and it's just so much easier to do this. The derivative is power down 12x squared minus 160x plus 400. Don't know if you can see that. Hope you can. I'll bring it back over here when we factor it. Maybe I should just rewrite it over here. Not sure if you can see that. So v prime of x equals 12x squared minus 160x plus 400. Now I want to set this equal to 0 so I can divide out a 4. And that's what I'm going to do. I'm going to go through here and divide everybody by 4 since I'm setting it equal to 0 to get me to this simple idea. I want 3x squared minus 40x plus 100 equals 0. I have to factor that. Now the good news, that doesn't look like an equal, does it? The good news is because of this, I already know that 10 was a 0. I saw it up here. So when I factor this, it's 3x, x. This is going to be a 10 because I know that x equals 10 was one of my bounces. And so this has to be a 10 also. Middle term, you'll notice, is minus 10 and minus 30. We nailed it. So coming out of here, when was the derivative of this function, the big function, 0? At x equals 10 thirds and at x equals 10. We cross that one out because it's an endpoint, and we know from our graph that that's a minimum in this closed interval. We know that this is x equals 10 thirds. And I can now go and talk about the dimensions, the optimal dimensions. So the maximum volume, you might write something like this, the max volume occurs at, and we're going to put the dimensions. And the first one is 10 thirds is the height. Now if you do this, 20 minus 20 thirds, well 20 is 60 thirds. So 60 minus 20 is 40. So 40 thirds and 40 thirds. Those are at these dimensions. We'll say these dimensions. What I'm trying to do here is show you that writing a function was really important, but not because of graphing calculators, etc. This happened, people did this hundreds of years ago before we had batteries, people. And it's the idea that calculus can get you to that particular spot because you can observe that at any turning point, at any of those standard max turning points, not an end point or something like that, the derivative is going to be 0 when you turn around. It is also, by the way, possible that you can turn around. Don't really want to put stuff on the wall because I don't want to confuse you, but you can turn around with a pointy point too. All right, and that's something Mr. Crawford's going to cover next year in either A, B, or BC Calc for you. So here you are, Mr. Mistakis on his YouTube channel, Muzz Math Rocking, up there. Buford was looking over the whole thing to make sure we did a good job. I have to paint this quickly because the family likes the hallway to look better. But ultimately, with the help of our BackHallProductions, you just got a chance to see what it looks like to use your calculus, okay? So I'm going to start painting, and somebody's going to turn the video off, or maybe I'll have to go turn it off. But basically, I just have to paint this over now. Takes about 5 coats, so I have to do it frequently, but they dry quick. You may not be interested in watching the whole thing, so you can turn the video off if you want to, anytime. It's not all that exciting to do this. I might leave it on forever so you can watch the paint dry. That'd be kind of cool. Try to get that first coat on real heavy. So everything, oh, and by the way, the blue really doesn't like to cover. That'll come back right through the paint. Again, if you're bored, turn off the video. I can't run over and turn it off. Somebody was supposed to turn it off for me, but they obviously have gone to do something else in the house. And Buford can't walk since the accident. So it's just me in the back hall doing some fun stuff. Gotta look out for drips too. Much easier to have a whiteboard at school. This is a bit of a fun one, but quick drip check. All right, I'll be doing this about 4 or 5 more times today. You should have a good day. Hopefully you're enjoying calculus.